altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and similar to each other. So this is just a one sentence statement here, but it's actually saying a lot. So it's saying that if we have a right triangle, BAC, okay, so that's our original right triangle, and let me just highlight that here so we can see a little bit better. So we have an original right triangle, BAC, and then we draw the altitude of BAC. So let me give BAC its right angle, and then we draw the altitude of it. In other words, we draw a line from the right angle to the hypotenuse, so it's the altitude is drawn to the hypotenuse. Okay. Now we have two, you can see that it's separated into two other triangles. So what this theorem is saying is that we have a total of really three triangles right now. So we have this one right here, I call that the small one, that's the blue triangle. We have the one on the right, I call that the medium one. Okay. And then the entire thing, BAC, is the large one. So the theorem here is saying really three different things. It's saying first that triangle BAC is similar to triangle BDA. Okay. So the big one, BAC, is similar to BDA. Then it's also saying that triangle BAC, so again, the original triangle BAC is also similar to the red triangle, which in this case is CDA. And then finally it's saying that the two triangles that we created, the blue one and the red one, are also similar to each other. So this is triangle BDA is similar to triangles CDA. Okay. And I'll explain soon enough how I got these names. Okay? So we got to be very careful how we name these triangles, because it's definitely going to affect our proof, and it is going to affect the way that we solve our problems. And so the way I did this was I started with angle B, then I went to the right angle. So in the smaller one, in the blue triangle, I also started with angle B, and then I went to the right angle, and then I went to the remaining one. Okay, so that's how I know that BAC is similar to BDA. And we have to be very careful in how we write these letters, because all of the angles have to match up, otherwise it doesn't work. Okay, so this is what the theorem is saying, and these three statements are the three statements that we're going to have to prove. Okay, so that's gonna be our next part. So I'm gonna pause right here, and then we are going to begin our proof. Okay, so I've redrawn the triangle before. It doesn't look really nice. It doesn't look quite like a triangle, but everything here is labeled correctly. So we're gonna start our proof, and the first thing that we are going to prove is that triangle BAC is similar to triangle BDA, and we can do this proof basically in 3 steps. Okay, so I'm gonna write it down here. Step 1, I can say that angle BAC is congruent to angle BDA since they're both 90 degrees. Okay, so I can say that angle BAC is congruent to angle BDA, because they're both right angles. Then I can say that angle ABC, so that's this one right here, and I'm looking at the big triangle right now. ABC, and then when I look at the blue triangle, the smaller one, is is congruent to angle ABD. Okay. So ABC is part of the big triangle, and then ABD is part of the small one, or the one that's shaded blue here. And this is reflexive. They're just really the same angle, just they're named a little bit differently, but they are. This is the reflexive property, not the reflection property. So this is reflexive property. And in our third step, we can say that since we have two angles congruent to each other, the two triangles have to be similar. So triangle BAC is similar to triangle BDA, and this is by the AA postulate, which says that if you have two congruent angles, then the two triangles must be similar. And there you have it. Proof in 3 steps that the smaller triangle here is similar to the big triangle. And I'm going to erase this and then proceed with the next part, which is proving that the red triangle is congruent to the big triangle. So we'll call this, the red one, the medium, and the entire one the large. Okay, so the second part of the theorem that we have to prove is that the big triangle BAC is similar to triangle ADC. I think a few steps back I might have said that this was CDA. It's incorrect. It should read ADC, and I'll correct that on the video. So we can do this by looking at the entire big triangle BAC and looking at the red triangle and identifying the angles that are congruent to each other. So similar to the last step, the last time we did a proof like this, we're going to start with the right angles. So I can say that angle BAC is congruent to angle ADC. So BAC, that's a right angle, and ADC, that's also a right angle. And there's also a theorem for this. This is called the right angles congruent theorem. Okay. Then looking at the big triangle again, you can see that angle BCA, so angle BCA is also congruent to angle ACD. So basically this angle C here, it's shared between the big triangle and the medium, or the red triangle here. So BCA is also congruent to ACD. Okay, and this is reflexive. It's the same the same angle that's being used again. And now since I have two angles that are congruent, I can say that the two triangles must be congruent. Because of the AA postulate. And now I'm done with this part of the proof. So I've done two parts of the proofs here. I've shown that the blue triangle is similar to the entire large one, and I've also shown that the red triangle is similar to the large one. And the final part of this proof is a little bit trickier. We're going to try to show that the blue and the red are similar to each other. Alright, so we get to the last part of this proof, and what we're trying to prove here is that triangle BDA is similar to triangle ADC. In other words, the blue one is similar to the red one. Now, you might be tempted to say that because the blue is similar to the entire right triangle, and because the red is similar to the entire right triangle, that they're somehow similar to each other, that there's a transitive property of similarity. I think there is a similarity, a transitive property of similarity, and you can prove it, but we haven't proved it yet, so we can't use it here. So we're going to use just a regular old proof to show that these two triangles, the blue and the red, are in fact congruent to each other. Sorry, not congruent, similar to each other. Okay, And we're going to start the strategy here is the same as it was before, which is to use the AA postulate in the end. And to use the AA postulate, we need to use two congruent angles. So I'm going to start with the two right angles. I'm going to say again that BDA, so that's this angle right here, okay, is congruent to angle ADC. And that's straightforward enough since they are both right angles. Now, what I want to show next, and this is a little bit trickier, is that I want to show somehow, let me erase some of this red and blue stuff so we can write in these angles a little bit better. So I want to somehow demonstrate that this angle right here, I want to show somehow that angle DAC is similar, or congruent rather, to angle DAB. So I want to show that DAC is congruent to DAB. Okay, so I'll make a note of that here. This is what we're trying to show, that angle DAC is congruent to angle DBA. I'm sorry, DBA. Okay, so I want to show that DAC is congruent to DBA. I already have one congruent angle. If I can show another one, then they have to be then the two triangles are similar by the AA postulate. Okay, so this takes a few more steps, but not too many. So first thing I can show is that BAD and DAC form right angles. Okay, so they add up to 90 degrees. So measure of angle BAD plus the measure of angle DAC is 90 degrees. Okay. And this is angle addition, and they're also complementary to each other. But you see that these the two angles that I reference, BAD right here and DAC, they form 90 degrees, so they have to add up to 90 degrees. Okay. Now looking at the blue triangle, you can see that angle BAD and angle DAC also form 90 degrees. Okay, so I can say that the measure of angle BAD, this one right here, and the measure of angle DBA, I'm sorry, DBA, okay, DBA also form 90 degrees. And my reason here is that it's the triangle sum theorem. So these three angles, 1, 2, and 3 here, oh, let me point it better, 1, 2, and 3 here, have to add up to 180 degrees, and this one's already 90, so the remaining two have to make 90 degrees. Okay, and looking at these two statements, I'm going to do just a little bit of algebra on them. So I'm going to take statement 2 and subtract BAD from both sides. So measure of DAC is equal to 90 minus the measure of BAD. Okay, and this is the subtraction property. Then I can say in this step here that the measure of DBA is also equal to 90 minus the measure of BAD, and this is the same answer as before. Therefore, these two triangles have to equal to each other because of the